Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 20th, 2026, just about 4 days ago. It introduces a novel paradigm that substitutes standard iterative optimization, like gradient descent, with direct constructive approximation. The paper is titled, Learning Without Training. And as we'll see later, the implications for bypassing the usual headaches of model initialization and local minima are really significant. To understand the mechanics, these matrices define the network's internal representation for the constructive approach. The first matrix, phi, organizes the activation of every neuron N across all M data samples, providing a snapshot of the feature space. Below it, the phi prime matrix captures the instantaneous rate of change for those activations. Instead of iteratively updating weights, the algorithm utilizes the algebraic structure of these matrices to build the approximation operator directly, which is how it guarantees convergence without traditional training loops. Well, to contrast with that new constructive approach, Figure 1.1 depicts the standard supervised learning paradigm that creates so many optimization headaches. The outer box represents the universe of all functions, containing the true target f, while the inner box is our limited hypothesis space. Ideally, we want to find p star, the best possible approximation within our model. But because we are limited to the noisy data cloud at the bottom, training usually lands us at p sharp, which is just an empirical estimate subject to local minima. So, contrasting with that optimization struggle, Figure 2.1 illustrates the proposed constructive paradigm. Here, we still have the universe of functions x, and the hypothesis space versus n. However, notice the vertical arrow rising straight from the data cloud. Instead of iteratively searching for a minimum, the algorithm directly constructs the approximation sigma n from the samples. This direct path allows the authors to mathematically bound the reconstruction error between sigma n and the true function f, completely bypassing the instability of gradient descent. Alright. Following the theoretical setup, Figure 2.2 presents the experimental validation. The left panel plots absolute errors against two baselines, the Nadaraya-Watson estimator and a radial basis function network. Notice the yellow spikes. The proposed method's error is strictly localized to the function's singularities. In contrast, the blue RBF error, which is actually scaled down by a factor of 1,000 just to fit on the chart, shows massive instability across the entire domain. Moving to the right, the cumulative distribution plot confirms this advantage. The blue curve, representing the new method, stays significantly lower, indicating much smaller log absolute errors for the vast majority of test points. Well, having seen the empirical results, Figure 2.3 visualizes the geometric intuition behind the proof. The blue dotted curve represents the unknown data manifold X sitting on the high-dimensional sphere shown in black. To approximate functions here, the method uses a tangent sphere, the red dashed line, which touches the manifold at point X. Because the kernels are highly localized, the authors can mathematically transfer approximation guarantees from the simple tangent sphere to the complex data manifold. So, while the previous figure gave us the geometric intuition, Table 2.1 formalizes the math. It defines the specific neighborhoods used to measure proximity, distinguishing between the standard Euclidean ball in the high-dimensional ambient space and the geodesic ball on the manifold itself. Notice in the definition column that the metric shifts. It moves from a simple straight-line distance to an arc cosine formula, which ensures that the approximation respects the curvature of the data's true structure. Alright, having defined the metrics, Figure 2.7 investigates the model's sensitivity to the parameter q, which estimates the manifold's intrinsic dimension. The vertical axis plots the root mean square error, while the horizontal axis tests different integer values. Notice the clear valley in the data points. The error is minimized specifically when q is set to 2 or 3. Since the true intrinsic dimension of this dataset is actually 2, this confirms that misestimating this parameter degrades the approximation quality. Wrapping up, the key takeaway is that we can substitute the black box of gradient descent with direct constructive approximation. This guarantees convergence and offers a mathematically grounded path to bypass the usual curse of dimensionality. That is it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.